thank you for squeezing into half a room. I'm not quite sure why. So we just released the 2018 temperature thing. We just gave a big press conference with NOAA. There was like 70 odd journalists and the like, and we got a big spread in the New York Times and the LA Times today. It's all very exciting. Even the Wall Street Journal was interested in what we had to say. So most of this work obviously is due to Reto, a little bit from Makiko, RV, who was now left for Facebook, Ken and Nathan, who's a graduate student at Lamont, and some of the other graphs are mine. So I'll just give you a summary of what we do and how that all works, just so that you're kind of in the loop, as it were, when people ask you about this terribly, terribly important part of our job. The interesting thing is that this is the most high-profile thing that GISS does, and it takes, I think we calculated it, about a half FTE a year, maybe a quarter of a half that FTE a year out of 100. So for 1/200th, 1/300th of our effort, this gets all the press. So let it know. Well, just understand. Yeah, no, well, yeah. I mean, like they didn't even know they were funding this for a long time, and, but now they just be aware that effort and reward are not linearly connected. Despite the fact that we do appreciate all the other efforts that go in, don't feel too bad when there aren't so many journalists asking to talk about other things. Okay, so if you aren't aware, the GISTEMP Index is something that we've been doing since the early 80s. It was written up by Jim and Lebedev's first name. What was his name? Sergei Lebedev. Back in the 1980s, has been revisited as interesting things happen. In papers since then, and we have a new paper that's hopefully in final review now. That Nathan is the lead author on, looking at an in-depth error analysis of what we've been doing for 40 years, which you might say is about time, but I'll give you some of the results from that in a second. Key things to remember is that all of the data sources that we use are all public domain. We're not using any secret source. We don't have any access to data that nobody else has, and most of the data, GHCN is put together by NOAA, which is why we couldn't do anything while we were in the shutdown. ERSST is put together by a different part of NOAA, and then there are stations in Antarctica which are run independently of my standing. It doesn't make sense. Which are run by a different organization. And the way that the methodology works is that we look at anomalies at each individual station. We have for each station there's about a 1,000-kilometer radius of influence, because we know that temperature anomalies are correlated over those kinds of distances, and we try and make a correction both for inhomogeneities in the weather stations and in the ocean data that's done by NOAA in both cases, but different parts of NOAA, and we have our own correction, well, not really a correction, but an avoidance of heavily urban areas when we're putting together the global means. The differences between what we do and what other groups do, and there's two main groups, and there's another two other groups that we could talk about. NOAA and the Hadley Center are kind of conservative when it comes to extrapolation into areas where there's no direct observations. And so their averages are averages just over the grid boxes where they have station data. The GISS analysis allows for more long-distance connections between stations, and so even if this grid box there is no data, you know, if there's data in this grid box here, then you know we allow that to bleed over. And that doesn't make a difference if the areas that you were sampling were not biased towards one temperature anomaly or another. But unfortunately, the main area that is not well sampled is the Arctic, and that's extremely biased in terms of the temperature changes that are going on. It's warming about 3 times as fast as the rest of the planet, and so if you only average over where you have data, there's a bias towards low temperatures because you're not including the areas where we know that the temperatures have been warming more. And I'll show you how that fits in later on. Okay, our kind of peak press thing was in 2016, like front page, like massive, like above the fold, very exciting. But of course, this year we're not the record year, and so this is just all in the past, basically. This is our result for this year, so it's red pretty much everywhere. Yes, it's warming, and in fact it's the 4th warmest year in our record after 2017, 2016, 2015. And in fact 2014, if you recall, was also a record warm year, and so the last 5 years in the record are in fact the warmest 5 years in the record, which is pretty impressive. If you look at the time history of this, you can see here this is back in the early 1900s, 19th century. You've got a bit of a peak warming around 1940, which some people would argue is more a function of bad ocean data. It might not have been quite so extreme. There were a couple of very warm years in the 1940s. There was a big El Nino in 1941 that really did make a difference. Then there was a pretty flat period through to the mid 70s, and then pretty much since the mid 70s, things have been warming up at a I don't want to say increasing pace, but have been warming up pretty steadily. This is 2016, and here's 2018. So here are the last 4 years. And if you draw a line, you say, oh well, you know, what's 1 degree above the late 19th century? These 4 years are all more than 1 degree above the late 19th century. So it's not quite pre-industrial, but if you were trying to compare this to, for instance, the IPCC or the UNFCCC 1.5 or 2 degree guideposts, I don't want to say targets, temperatures to avoid, you know, we're well above 1 degree now, and we are unlikely to go back down below that.
Gavin, is there anything special in 1910 dip?
Well, there's a volcano in here, but no, not sufficient to produce that in and of itself.
Why do you decide on the baseline year? Like,
it's totally arbitrary.
Okay.
So the baseline that we use is 51 to 80, and Rado could tell you what the history was, but we started in 1981, and that was the last 30 years. As we've gone forward, it seems more sensible to keep the baseline the same instead of changing it all the time, because we're not really interested in giving people up-to-date estimates of what the climate normal is, but we're just trying to keep track of what's going on. Now, you know, you might usefully ask, you know, is this the best baseline to be talking about it in public? And the answer is no. It's totally arbitrary. And so in public, I've started mainly focusing on a baseline that's focused on the late 19th century. So that seems more sensible. And then these numbers here, you know, this would be 0.83, but it's like plus 0.22, so this would be like 1.05 or something on that baseline. This is including the seasonal anomalies. So this is the seasonal anomaly with respect to the annual mean. So as you might expect, Januaries and Decembers are colder than the annual mean. Julys and Augusts are warmer. And the colours go through time, and so it makes a very pleasing rainbow because, you know, the red colours are at the top. And so this is 2018 data points. Some of the summer temperatures were quite close to the record warms, but you can see, for instance, like in the this is 2016, 2017. So you know, the winter temperatures that we've had in the very warm years are still significantly warmer than we had in 2018. These are the patterns for the top 4 years. There are obviously variants. You can see, for instance, you know, El Nino, La Nina. So we're seeing the record years go through ENSO cycles. The big thing that you notice, of course, is that it's always red in the Arctic. And the kind of more interesting thing, perhaps, is what's going on in the North Atlantic. So in order, right? So this is 15, 16, 17, 18. This is a persistent feature, and you know, people who are looking at the overturning stream function and the ocean changes, you know, this is indicative of a slowing of that heat pump.
The Gulf Stream is also stronger. The year where that
right, yeah. So what's happening is that the extension of the Gulf Stream is not extending as much as it used to.
Is the OSNAP functional now?
Yes.
Yeah. So yeah, but OSNAP is up here. But they have 18 months of data, so it's not really enough to see what's going on in terms of the trends. And the rapid array is down here, which is not really seeing, which is not really necessarily relevant for what's going on a little bit further up north. The other pattern that's obviously quite interesting is the north-south pattern. So the absence of warming around the southern oceans persists, and at some point it will go away. But for the time being, it's still the slowest warming part of the system.
In Antarctica, that's real. There was no change in 16, 17, 18, and now it's all red.
There's a lot of A. There's not very many stations, and B. There's a lot of variance. So if you look at if I applied this with the uncertainties, you really wouldn't see very much. I'll show you like the long-term trend pattern. You'll see it more clearly. Now this is new and kind of interesting. So the people that work on the AIRS infrared sounder at Greenbelt emailed me like last year and said, hey, well, you know, why don't we compare the trends that we get for ground temperature anomalies? So what they're sensitive to is the actual ground. You know, our analysis is nominally for the surface air temperature, but they can detect the ground temperature. So there's a difference, obviously, but they can detect the ground temperature everywhere, and they can then like look at the anomalies. So the absolute numbers are quite different to the surface air temperature, but the anomalies are actually very similar. And so this is the anomalies that you see in, like, so this is the 2003 to 2018 trend. So it's only 16 years, and we can compare it to the GISTEMP trend, which is exactly the same time period. And what you can see is the patterns correlate very strongly. And when you do the correct smoothing and you do the correlation is about 0.75. And on a month-by-month basis, you know, it varies a little bit depending on what's going on and what the cloud clearing algorithm is doing. But the average correlation on a month-by-month basis between our analyses and a totally independent remote sensing product is around 0.7, which is pretty nice.
What's the AIRS temporal resolution?
I'm sorry?
What's the AIRS temporal resolution?
So it does. It's in the A train. So it's like 16 loops over a month or something. Twice a day. Yeah. So they have to make some. There are some gaps, but over the month it fills out quite nicely. So this paper is in. So if you're interested, it has like a whole big analysis of what the AIRS data is actually saying. Joel Susskind.
Joel Susskind. Is it in what journal?
It's in Environmental Research Letters. I'll send you. Well, because they want, like, we tried to get it in GRL, and we got some idiot reviewer who just wouldn't let it pass. And so they said, well, you know, you could go to this totally obscure AGU journal that nobody ever heard of. And we said, no, F you, and stormed off to
Gavin said he's errors measurement. Are those day and night?
I think they're like 2 o'clock in the afternoon.
So yeah, 1:30 I think in the afternoon, 1:30 in the morning.
Yeah, so I think there's 2 a day.
Yeah, but day and night.
I think 1:30 in the afternoon.
Yeah, no, there's
one
something.
day and one night.
So,
But is there a difference?
but there is that. I mean, obviously there is a difference in the diurnal cycle is changing in non-stationary ways. So the minimums are warming up faster than the maximums, and so you're not really you're not seeing that. But then again, like, you're looking at ground temperature, which is more stable than air temperature. So.
But do you have that plot for day and night?
I don't. It might be in the paper. I don't. I will forward you the paper, and you can then ask Joel about those kinds of things. I have no idea. So if you look at the long-term trend, so this is like 1970 onwards. You know, it's remarkably clear. There's more warming over land than there is in the ocean. There's more warming in the north than there is in the south. More warming in the Arctic than anywhere. And so when you get down here, you know, to Antarctica, the only place where there's a very, very clear and robust warming signal is West Antarctica and the Antarctic Peninsula. The rest of it is very, very noisy, and partly that's a sampling issue, but partly it's because it's just not very. It hasn't warmed there yet, but it will. People ask about the El Nino impacts on the global mean temperature, which I think is actually a topic that might be usefully looked into more deeply. But if you classify years according to what their ENSO index is at the beginning of the year, that turns out to have a very high correlation to the anomaly around the trend. Right? So take out the trend, you're left with an anomaly. Those anomalies are very highly correlated, like 0.66 or something, to the ENSO state at the beginning of the year. Right? It doesn't matter, like in the summer it's too late and it's small anyway, and in the winter it doesn't have enough time to really make a difference. And so there's like a 2 or 3 month lag in terms of how the atmosphere responds to an El Nino event that involves actual advection of heat out of the tropics. It involves changes in water vapor, changes in the radiative fluxes associated with those changes in water vapor and clouds. Anyway, so what you end up with is that when you have an El Nino year, you tend to have a higher than trend anomaly, and when you have a La Nina year, it's the opposite. And if you do the trends on El Nino years and trends on La Nina years, you get the same trend. It's just that they're kind of offset by about 0.2 degrees. So 2016, there was a whopping El Nino event that occurred that pushed you above the trend there. 2017, it was pretty neutral. 2018, we started off with a slight La Nina phase, and so that kind of pushed it down. 2019, we're starting with a slight El Nino phase, so that's going to push it up. So 2019 is going to be warmer than 2018, barring some massive volcano that happens in the next 3 weeks. And so by the time by next year, the headline will be the same. The top 5 years, the top 5 warmest years in the record. It gets a little repetitive doing these press conferences. So
Say 6. Top 6 years.
It's all like your top 6 years, yeah.
Do you have January yet?
Do we have January yet? We haven't processed January yet. One of the things that I like doing just for fun is demonstrating how predictable the annual temperatures are. If you predicted 2018 based on just what ENSO was in December and January at the beginning of that year, this is the estimate that I came up with, which actually was exactly right. Yeah. And then there's other estimates you can do, like based on the the year to date, right? So if you have like 6 months of the year, then you can predict what the total year is going to be, because obviously you already have 6 months of it, and then you can just kind of make a prediction about how persistent that is. And these are the estimates that you get. This is in February, so after 2 months of data, we were able to still predict within the bounds of uncertainty what we would get by the end of the year. And obviously, by the time you get to July, the error bars are small, and you can make a pretty good estimate of what the annual temperature is going to be. So we did pretty well there. And this is 18, and you can see. So, for instance, at no point did we suggest or did we predict that 2018 would be a record warm year, and indeed it did not turn out to be the case. So you can predict. So it's odd because it's not really climate. It's not really a climate prediction, but it's not a weather prediction either. So it's kind of somewhere in between. But you can pull information out of these things. If you actually just take out that ENSO signal, which you can do just by kind of regressing out the part that's associated with ENSO, you can come up with an ENSO corrected data series, which is the red line, compared to what I showed you before, which is the black line. And you can see that the variance is smaller. There's still interannual variability, but most of that interannual variability is associated with ENSO. And what it does is it actually enhances the signal associated with the big volcanoes. So now you can see this is the Mount Agung, this is El Chichon, and this is Pinatubo. Because if you look at El Chichon and Pinatubo, there was an El Nino that happened very shortly afterwards. May have been connected, may not have been connected, but that obscures the global cooling that you would have got. And so you can see the global cooling from volcanoes more clearly when you take that out. And if you do that, you would have found that 2018 would have been the third warmest year as opposed to the fourth, and the warmest year in the ENSO corrected database would have been 2017, not 2016. If you look at what other people do, and they make different assumptions about the data they ingest, how you deal with inhomogeneities, how you interpolate over data poor areas, how you stitch things together over sea ice. It turns out that none of those things really make any difference at all. Right? So the warming that we're seeing in our record is extremely robust, and it's basically the same warming that you see in all the other records. And for people who are still counting, this is the hiatus.
But I guess now that the Arctic warming is in full sway, GISS will always be the warmest of the various estimates.
Yeah, so Cowton and Way and Berkeley Earth also do an interpolation into the Arctic using various methodologies, different methodologies. And so what tends to happen is that those three kind of group themselves, and the Hadley Center and the NOAA record are slightly cooler. Though the Arctic temperatures last year, they're still much warmer than the global mean anomalies, but they're down a little bit from the maximum that they had in 2016. I mentioned that Nathan, who was a grad student in stats and is now a grad student in D's, working with Lisa Goddard, has been working on a kind of end-to-end uncertainty analysis for the whole GISTEMP procedure, which includes taking the uncertainties from the GHCN groups, taking the uncertainties from the SST groups, understanding the uncertainties in our model, in our procedure, and then kind of using the reanalyses to estimate the errors that you get from the spatial sampling as you go back in time. Anyway, so we end up with a total error, which is there's a couple of things that are missing, but basically this is pretty good. A total error for the recent annual means of about 0.05 degrees Celsius. That's pretty low uncertainties. And going back, when you get back to the 19th century, it's about 3 times that, 0.15 to 0.2 degrees C. Which means that our ability to confidently state that we are now in a much warmer place than we were it's without question that that's the case. Unequivocal, as they say. So this was fun. So in 2014 we did this analysis, and 2014 was the first new record that we'd had since 2010. But 2014 in our record was only a little bit warmer than 2010. Right? It was clearly warmer, right? I mean, so and we had a little bit of a discussion at the time. So how should we describe this? You know, should we describe this as being statistically tied? Well, you know, it was larger than like noise, but not large enough that the uncertainties in the analysis couldn't mean that, you know, in the real world maybe 2010 was slightly warmer than 2014. And so we put out a press release, and this didn't work because I just put it in PDF. Anyway, but then the Daily Mail, like the week after, had a thing. NASA climate scientists said that 2014 was the warmest year on record, but they're only 38% sure that they're right, because that was our estimate of how likely 2014 was to be the warmest temperature compared to 2010, which only had like a 20% chance, and 2005, which had a 5% chance. And we explained all this in the press briefing, which the Daily Mail did not attend. Anyway, the story next week was that we'd hidden this, or that we hadn't told anybody when we really had. And the funniest thing was that they found a photograph of me, which I think had been taken by Christie a while back. Anyway, but and they captioned it. And you probably can't read it. Anyway, it says, Gavin Schmidt of NASA's Goddard Institute of Space Studies admits there's a margin of error. A scandal. A scandal. Yes. So they didn't attend this year's briefing either. Don't know what they're going to do this year.
Just wait a week.
Yeah, maybe. So the interesting thing is that with the new uncertainty analysis that Nathan has done, we can actually answer that question more precisely than we were able to in 2014. And so this is, you know, so these peaks here are estimated PDFs for the true temperature anomaly in each of the years that we considered a record, right? So you know, here's the 1940s, 1980s, 2000s, here's 2010, and 2000. Well, this one's 2010, this one's 2014. So you can see they're quite close. But you can actually now do the integral of the PDFs and where they cross over and where they don't cross over. And with Nathan's new error analysis, it actually turns out that we should have said that 2014 was 74% more likely to have been the record than 2010. And the records that we saw in 15 and 16 were totally unequivocal.
You written to the Daily Bid?
I should send that to the Daily Mail. Yeah. Told you. Anyway, so the right now the probability of the warmest year, you know, it's almost 100% that in fact it was 2016. There's a tiny little bit of overlap with 2017, but not enough to really talk about. So I think that might be it. That was it. Oh yeah, there we are. Consider yourselves all brought up to speed. But if there's any questions, I'll be happy to.
So now that we've